An empty p orbital is a chemical crisis. Without electrons to balance the positive nucleus, it forms an unstable void that will pull electron density from any surrounding structure to reach a lower energy state. Most students approach organic chemistry by cataloging these instabilities on dense, handwritten sticky notes, relying on sheer repetition to get through exams. This specific 13-part stability sequence is often presented as the definitive hierarchy of carbocation behavior. The chain at inequalities stretches across the page, implying a single, unbroken progression from most to least stable. Relying on this list as a static artifact limits your ability to predict how a novel molecule will react in a laboratory setting. This sequence is an empirical record of charge delocalization, governed by competing physical forces. We can analyze this entire progression by dividing it into 4 distinct physical tiers. Transitioning from memorizing the order to evaluating the underlying physics allows us to identify the laws governing the stability of any intermediate. At the lowest stability end of the sequence, we find simple alkyl, vinyl, and alkynyl cations. To exist at all, a carbocation requires adjacent electron density to partially offset the positive charge of the empty p orbital. In this first tier, the stability is dictated by the s character of the carbon atom holding the charge. We can see this shift from the tetrahedral sp3 orbital to the trigonal planar sp2, and finally to the linear sp orbital. The sp orbital pulls the electron cloud significantly closer to the nucleus, resulting in a shorter, more compact orbital. Electrons held this tightly increase the effective electronegativity of the carbon. The atom resists donating its own electron density into the neighboring void. Placing a positive charge on a highly electronegative sp carbon creates a state of maximum thermodynamic instability, which is why these structures anchor the bottom of the list. Moving further left into the alkyl groups, we see the first significant increase in stability. This jump is driven by hyperconjugation, the primary stabilizing mechanism for saturated alkyl chains. Hyperconjugation occurs when filled sigma bonds, like carbon-hydrogen bonds, align parallel to the empty p orbital. This alignment allows electron density from sigma bonds to spill over and overlap with the p orbital. The stabilization depends on the number of alpha hydrogens. A tert-butyl cation has 9 distinct sites where this donation occurs. Tertiary cations with 9 interactions beat secondary cations with 6 and primary cations with 3. Hyperconjugation demonstrates that a high volume of relatively weak interactions can effectively dilute a localized charge. Tier 3 involves pi resonance, where the charge is shared through overlapping p orbitals. This is usually considered a far more powerful stabilizer than hyperconjugation. However, the empirical data on this note highlights a specific case where that assumption is incorrect. The non-resonant tert-butyl cation actually outranks the resonant benzyl cation. In the benzyl cation, the empty p orbital overlaps with the pi system of the benzene ring. This allows the positive charge to be distributed across 3 different positions within the ring itself. If resonance is typically considered the stronger force, why does the tert-butyl cation remain the more stable intermediate? The answer lies in the cumulative effect of the 9 hyperconjugating bonds in tert-butyl. The total electron density donated by 9 sigma bonds is mathematically greater than the stabilization provided by the single pi system of a benzene ring. Resonance only regains its dominance when the pi system is expanded. By adding a second or third phenyl ring, the resonance network grows large enough to easily surpass the limits of hyperconjugation. Generalizations like resonance always beats hyperconjugation are inaccurate. Actual stability is a product of the specific volume and overlap of all available quantum effects. At the far left of the note, we reach the highest level of thermodynamic stability possible for a carbocation. This tier features the Tropylium Ion, which achieves its stability through aromaticity. Here, the empty p orbital provides the final link needed to complete a Hookeau 4n+2 pi electron system. Because the path is complete, electrons circulate across the entire 7-membered ring, resulting in total delocalization. Even so, the tropylium ion is surpassed by the tricyclopropylmethyl Carbocation. This molecule utilizes Walsh orbitals, strained bent sigma bonds in cyclopropane rings. Due to high ring strain, these bonds are forced outward, taking on a shape that allows them to behave like p orbitals, creating massive overlap. This specific powerful interaction is known as sigma conjugation. Combining 3 cyclopropane rings creates an electron donation network that is actually more effective at stabilizing charge than aromatic resonance. At this level, molecular geometry is used to bypass standard orbital rules and reach unprecedented levels of stability. This handwritten note is a record of how electrons distribute themselves to minimize energy. It represents a gradient of delocalization efficiency. On the right, electrons are held in tight, localized orbitals within electronegative systems. On the left, we find expansive networks where charge is shared across dozens of atoms. Understanding these 4 tiers moves the study of chemistry from a 2-dimensional list into a 3-dimensional analysis of orbital overlap. This hierarchy is not a collection of individual exceptions to be memorized for a single exam. By integrating the effects of hybridization, hyperconjugation, and resonance, you can evaluate the stability and reactivity of any molecular intermediate.